Let's do a summary of how to use Fourier series to solve the boundary value problem solution. And let's code it into the MATLAB and compare to the exact solution to see whether using Fourier series expansion to represent the solution of boundary value problem, either that is accurate or not. So we use an example, which is y double prime plus 4y equals to 1 with the homogeneous boundary conditions. We can solve the exact solutions using both the homogeneous part and the particular solution part using undetermined coefficient can get this exact solution, okay? And you can see the note how this exact solution can be derived with. It's very simple for this one. We have derived undetermined coefficient for many times, so we don't detailedly say here. Then we talk about using Fourier series to solve the BVP to get these solutions. As a summary, what we did here using Fourier series, first step, we are trying to solve this y double prime plus 4y equals to 0, which is the homogeneous part of the boundary value problem. The homogeneous boundary condition is still the same, y0 equals to 0, yl equals to 0. And first, we need to check for this part whether they are a Sturm-Liouville problem or not. If they are Sturm-Liouville problem, then we can derive our Fourier series. If they are not, then we couldn't use Fourier series to represent our boundary value problem solutions. So first we check, okay, they are Sturm-Liouville problem. Okay, if yes, then we can get the eigenvalue and the eigenvectors of this Sturm-Liouville problem. Okay, so we get our lambda, which is unlimited many eigenvalues. Each of the eigenvalue will correspond a unique eigenvector, so we get infinitely many eigenvectors as well. Then the non-homogeneous part, which is y double prime plus 4y equals to 1, we can assume the right part fx equals to 1. This is a continuous function in between the boundary values, which is y naught equals to 0, yl equals to L. So even though it's not fitting into the boundary conditions, we can still using continuous function. I mean, we can use the Fourier series generalized format to represent the continuous function fx equals to 1, which we already solved that part. Then we are trying to use the Fourier series to represent both the y prime, y double prime, and the fx into our original ODE and trying to get the coefficient part out. So there we assume that since we derive the eigenvalue and the eigenvectors, we assume the yx will be equals to the sum from n equals to 1 to infinity bn sine n pi x over L, which is the yn part. We assume this yx, we derive the y prime, y double prime, we get the left-hand side, which is y double prime plus 4y, represented by the generalized Fourier series. The right part, which is fx equals to 1, we also use the generalized Fourier series to represent. Then we get solve our bn, which we can integrate our solved bn into our back solution yx. So yx is finally this format. And now we are trying to code this yx using generalized Fourier series expansion and compare with our exact solution, which is here using MATLAB. Okay. So let's see the MATLAB. Okay. So this is the MATLAB example. We are trying to code both the exact solution as well as using the general Fourier series expansion to represent our BVP solutions. As per usual, we will clear out, close out all the figures, clear all the data we have before, and we will set up the X domain, which L equals to 3, the same as before. We set up 200 points in between 0 to X, L, which L equals to 3. We can calculate what is the exact solutions which is represented by the YE part. So we get our exact solutions. Then we are trying to calculate the Fourier series approximation to represent our our approximate boundary value problem solutions. And we define the coefficient, we define the range of our Y sum term, which will be all zeros corresponding to each X values in between 0 to L. That is just initial values. Then later we will update this sum term with each looping term added into the sum term. Then the maximum number we will run is 100. You can change to 50. But you can just set up a reasonable number here. The maximum number you will run in the while loop. You set up a tolerance so that the relative change of the S step as compared to the whole sum, if that is smaller than the tolerance, that means the S term value is really small. You don't need to care that much. Then you can stop the looping. However, if the relatively change by the S term on the overall sum is bigger than the tolerance, then you still run the loop. So this is very similar logic as how we code in the power series. We set up the initial relatively arrow, which is 1. Any number bigger than the tolerance is fine. We set up an initial looping term is 0. So the initial step will be 0 step. Then we run the while loop. When the arrow is the relatively change of the S term is bigger than the tolerance, or the number of our iteration is smaller than the maximum number we set up, it will run for the while loop. Any of the terms satisfy, it will be exit the term. For example, the relatively change is smaller than the tolerance, or the looping of the looping number is bigger than the maximum, then it will exit the while loop. So we first update our number. So the first iteration will be n equals to 1. And we only care about the odd term because only when odd term that y is now equals to 0, or the s iteration for the Fourier series is now equals to 0. Then we update at that n step. The generalized Fourier series term is equals to this long term we derived before, and we will update the sum term with the running items. So we will update our sum term with the Fourier series at nth iteration, and we are trying to find, okay, the relatively change of nth term as an impact on the overall sum. If that impact is big enough, then we still running the loop. However, if that relatively change is small impact, smaller than the tolerance, we will exit the while loop. Then we can plot the exact solution as well as the generalized Fourier series representation for the Y solution, and compare whether they are similar enough or similar or not. So if we run, we can generate a picture, which is a comparison between the exact solution with the Fourier series represent solution. You can see they are overlapping to each other. With the maximum number 100 run, you always can track how many run you have, how many steps you have run for the you have included for the Fourier series. But overall, the point we want to say here is that we can use Fourier series expansion to represent our BVP solution if the BVP is falling into the part where that the homogeneous part is student-Duval problem, and we can use Fourier series expansion to represent our BVP solutions, and they are pretty well aligned with the exact solution.